Hi everybody, Miss Wiesen here. We are getting ready to start our 7th unit in AP Chemistry, which is covering concepts over chemical equilibrium. So let's go ahead and title our unit note guide so we stay organized, Unit 7. Additionally, you should have anything out that will help you take notes like extra paper, your AP reference sheet, and a calculator. So chemical equilibrium, this is by far one of the most important concepts in our course outline for AP Chemistry. You're guaranteed to see multiple choice questions and at least one FRQ relating to equilibrium. At this point, you guys, in chemistry, you might have been led to believe that when a chemical reaction occurs, it goes to completion. So if you look over here to the right-hand side, a generic reaction I wrote, all reactants A will form products B. Well, what if I told you that's a lie? That most chemists would argue that actually chemical reactions don't go into completion, but rather go until there is this establishment of an equilibrium. So what I'm telling you is that most chemical reactions are, in fact, reversible. And I put that down here. Reactions are reversible, okay? So there's a couple of things that you can see here. You could see potentially that in a chemical reaction where the forward reaction is favored, and then maybe the reverse reaction not so much. You could see another scenario where the forward reaction is not favored as much as the reverse reaction, or they could be favored equally, okay? So now I want you to be clear that we don't write arrows big and small like I have showed you to the side. All right, let's look at the definition here. I'm going to go ahead and highlight it. Equilibrium is the state where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, and it's at these conditions, the concentrations of the reactants and products will remain constant with time. And once that equilibrium has been established, it's going to be done so at a constant temperature. Okay. Another important thing that I will probably touch on multiple times, but never at the last sentence of that first paragraph, never forget that equilibrium is temperature dependent. Okay. So let's talk about what dynamic equilibrium is. Okay. The word dynamic in itself means it's constantly moving or it's not static. It doesn't remain as is. It's changing, right? Dynamic means changing. So what is dynamic equilibrium? Well, again, these double arrows are going to indicate to you that the reaction can proceed in the forward and in the reverse simultaneously. And eventually, equilibrium will be established in that reaction. And it's important to note that the rate of each direction is going to be equal. The rate. Remember, we did rate laws. So don't confuse rate with concentration, okay? It's related, but rate is not concentration. This also keeps the concentration of the reactants and products constant. So now, once we do get the constant rate, or once the rate is equal, then we know that the concentration of the reactants and products are going to be held constant. Okay, remember when you hear the word constant, that does not mean that it's equal to 0. Okay, it does not mean it's equal to 0. Okay, so if you're doing a reaction, for example, and you've got 0.5 molarity of a reactant and it's all of a sudden equal with 0.5 molarity of the products, those two concentrations are equal. That's not what this necessarily means, right? Oh, sorry. You could have a reaction where I'm doing hypothetical concentrations. The reactants are at 1 molarity, and at equilibrium, maybe the products would be, 0. Maybe the reverse reaction's favored completely, and that's the equilibrium that has been established, okay? Anyway, let's go into a little bit more detail on all of this. One thing that you might remember is that in chemical reactions, when you're starting off with a reactant, if we've got concentration on my y-axis and I've got time on my x-axis, that we're always going to, at the onset, right at the initial onset of a chemical reaction, we'll always have the highest amount of reactants. And over time, we would expect that concentration of the reactants to decrease. Now, if we saw a reaction like this, and let me change my color on my line to make it stand out a little bit more. If we had a reaction that actually went to 100% products, our curve would look like this. So this would technically be a curve of an irreversible reaction, meaning only the forward reaction would be favored. And that's because all of our reactants are forming into the products. Okay, I just told you though, that's not really what happens. In fact, oftentimes that's not the case. In fact, let's take a look at a plot that shows us a reversible reaction curve. Okay, here's an example. I'm going to go ahead and this is the example right here in your notes. It says, look at the following plot of the reaction between steam and carbon monoxide. It looks like this is happening in a closed vessel at a high temperature. Okay. So take a look at this plot, and actually it is right here. It's not right next to it, so I apologize. Okay, so I'm going to go ahead and just write the chemical reaction that's occurring directly above the plot so I don't get confused. But it says steam and carbon monoxide. Remember, you guys, steam is just gaseous water, so H2O. And then it says plus carbon monoxide plus CO. And it looks like in this particular reaction, and so this is a reversible reaction, so I'm going to make sure I draw my double arrows. It looks like we'll have diatomic oxygen, or excuse me, hydrogen, and carbon dioxide gas. So here's a reversible reaction curve for this reaction that I just wrote above it. And let's go ahead and do a quick review. This should look a little bit familiar from our kinetics unit, but if you look at the y-axis, our concentration, I don't know, we'll just kind of arbitrarily put 1, make it easy and simple with easy numbers, and down here would be 0. And so go ahead and take a look at these curves. There's a red curve and a blue curve. Which one would represent the reactants and which curve would represent the products? Can you take a guess? That's right. If you said that the red line was the reactants curve, then you are absolutely right. And then obviously, let me just go ahead and label the blue curve as our products. Okay, and just let's go ahead and explain that one more time. Why? Because at the onset of a chemical reaction, we are assuming we have 100% concentration of our products. And as time goes by, the reaction is allowed to proceed, and the concentration of our reactants decreases because they are forming into products. There is going to come a point, though, that this curve seems to flatten out, or plateau, you've heard me say before. Okay, so let's explain why does the product curve look like this? Well, right at the onset of a chemical reaction, we technically don't have any products formed yet. And as the chemical reaction's allowed to proceed over time, of course, we would then expect the concentration to increase. Notice again that at some point, the curve of the products flattens out, okay, at a constant value, a constant concentration at a certain time. All right, so why? What's going on here? Why does this, or how does this represent a reversible reaction curve? Well, let's take a look at the blue line first, the products line. Why is it that this products line flattens out? If we had to go over here and kind of guesstimate the concentration of our products when it starts to plateau, oh, I don't know, what would you call that, 0.6 or 0.7? Okay, why does that not go why does the product's concentration not go all the way to 1? That's right, because the product concentration doesn't ever go to 100% or 1 in this case, because those products are actually reforming back into the reactants. So products reform to reactants. Okay. Now let's go ahead and take a look at the red line, our reactant line. Why is it that once our line becomes constant and it plateaus, how come that never goes to 0? How come we never get rid of and convert all of our reactants? Well, since this is a reversible reaction curve, we can assume that the reactants here will never go to 0 because the products are forming back into the reactants. So products form back to reactants. Okay. All right. And you can see here one important thing that this unit's going to touch on quite a bit is there is a certain time. You can see me circling here. It's time at which equilibrium was established. Okay, so this is one common equilibrium curve or equilibrium position that you will see. Here is a second one. I'm going to go ahead and just write it up here. If, again, concentration's on our y and time is on our x, you have a curve where your reactants go like this, and your products will go like this. And you will even have a curve that can look like this. Now you'll have your reactants and your products. Okay, this one's pretty rare, but it happens. So take a look at each of these curves. Can you give me a brief summary about what is happening to the reactants and products in each one? So those are your 3 different types of equilibrium positions that can occur. All right, if you need to process that, go ahead and pause me. I would also like in your explanation, if you can, where is our time of equilibrium establishment on these 2 new curves that we drew? All right, so let's keep talking about this thing called the equilibrium position. If a reaction lays far to the right or goes to the right, then we're going to be favoring the products, right? Those reactants are going to more readily form into those products. And in other words, if the reaction lays or goes to the left, it's going to favor the reactants, okay? And when this equilibrium position is established and how it does so, it's going to depend on 3 main factors. The first thing that's going to depend on the equilibrium position of any particular reaction is the initial concentration of the reactants that you're starting with. Remember, we learned when we were learning the collision theory that if we have a higher concentration of the things reacting, you're going to have a potential for more collisions and have a faster reaction. Okay, the second thing that depends on the equilibrium position is the relative energies of the molecules or substances reacting and being produced. And then the third thing that's going to affect the equilibrium position is, we say, the degree of organization of the reactants and products. And remember, that is basically the position or orientation of the substances. Let's go back up to number 2. When we talked about energy, we learned about energy in thermodynamics, and we measure energy in kilojoules per mole. Okay. Oh, and let's go back up to 1. I apologize. Initial concentration. Remember, in rate laws, we wrote initial concentration. You always see brackets. And if it's initial or at the onset, it's usually we put a little subscript 0 down in there. Okay. You are going to see an equilibrium constant, and it is going to be represented with an uppercase K. Okay. Oops, that's a little dark. That's okay. If K has a value of greater than 1, that's going to mean that the reaction is going to favor the products. So does that mean that the reaction is going to lie to the right or to the left, you guys? That's right. It's going to lie to the right. It's going to favor the right. All right. And if K is less than 1, so a really small number, then that means that whatever reaction you're talking about, the reactants are going to be favored, and therefore our reaction will lie to the left. Okay, does that make sense? Hopefully you can start seeing the language being used and are comfortable when you hear it. Another thing that I want to just highlight here, if K is greater than 1, then generally speaking, our K value will be a positive number, positive K value. And if K is less than 1, then we can definitely get a negative K value. Okay. And if you want to, I can just represent this sentence in a little generic formula. So if K is greater than 1, then A would favor B. And if K is less than 1 or really small, then B favors A. B to A is favored, rather. Okay. All righty. Let's keep moving on, you guys. All right, let's talk about what the equilibrium expression is. Okay, equilibrium expression doesn't sound as fancy as it is the wording here, but it's a general description. Oops, I did my highlighter. It's a general description of the equilibrium condition that is present, okay? And in 1864, of course, you had some scientists who established the general rules behind equilibrium expressions here, okay? There it is again. Equilibrium is temperature dependent. So again, that's the second time this has come up in the first page of notes. So we'll have to make sure we keep that in our file warehouse memory. Let's just take a general example, all right? We are learning about, we're learning how to write the equilibrium expression. And let's take a look at this generic reaction that's written in the notes here. Remember the difference between a lowercase, let's just say, for example, the lowercase a versus the uppercase a. Do you guys remember what that means? Yeah. The lowercase letter would represent the coefficient, and the uppercase letter would represent the substance itself, the formula of the substance. So clearly I have two reactants, and they're forming into two products, and it looks like this reaction is reversible. And what you notice down below is that if I wanted to write the equilibrium expression, I am going to need to consider and set it equal to the equilibrium constant K. We did talk about K just a second ago. Don't worry, we'll keep talking about it. But if we're trying to figure out our equilibrium constant, okay, what is K? What you then need to do is take the chemical reaction, and in this case, here's the generic one that they are writing the expression for. So take a look and tell me, what are they doing here? They've obviously set up the equilibrium expression where our products are in our numerator, and it looks like the exponent or the superscript is being raised to whatever the coefficient is, okay? And then our reactants are in the denominator, and again, the coefficients of those substances are being raised, okay, in the expression. You can see it here. Now, oftentimes in literature, you'll see the equilibrium constant K written just as K, or K sub C, or KCQ. Be familiar that they all mean the same thing, but they can be represented in multiple different ways. I will tell you that the one that you most commonly will see is EQ. Alrighty. So your general format, one more time to recap, the general format of how you write an equilibrium expression is you set it equal to the equilibrium constant, K, and we'll be figuring that out. We could solve for that if we have the information contained in that expression. You put your products in the numerator, raise each of your products to the coefficient, and then, of course, your reactants are in your denominator. So that is your general format on how you write your equilibrium expression. Don't worry, we'll get some more practice here soon. Okay, keep on going. Page 2. All right, the product concentrations appear in the numerator and the reactant concentrations appear in the denominator. Each concentration is raised to the power of its coefficient in the balanced reaction. Boom, there it is. Just what I said several times is put into writing right here, okay? And again, I kind of gave you guys a list of some symbols to look out for and to know. Again, brackets mean molarity. Please don't forget that. You can see here when they actually use the specific equilibrium constant expression. It'll use K sub C for concentration, K sub P for pressure, and then just normal K, just generally speaking. K is oftentimes going to be written without units. So just so you know, there is a K for everything, pretty much. All right, let's go ahead and see if we could use talk about these equilibrium constants a little bit more and see if we could actually use them. Okay, so remember, this is one thing that you're going to just need to know. If you have a chemical reaction where you have a pure solid, okay, or a pure liquid, go ahead and take a second and read how it will not appear in the equilibrium expression. Again, pure solids and pure liquids will not be included in the equilibrium expression. Okay, they go on to say that water is a pure liquid, water as a pure liquid, when it's used as a reactant, it will not appear in the expression. All right, let's read a couple other tidbits about the equilibrium constant. And then we'll do some practice problems. Remember, if you could do the practice problems ahead of me before I get there, that would be wonderful. All right. Weak acid and weak base equations are heterogeneous, multi-states of matter, pure liquid, and aqueous components equilibrium. And the solubility of salts are also going to fit into this category. Okay. The initial solid component has a constant concentration and is therefore left out of the equilibrium expression. So these are some just additional factors that we need to consider when we're writing our equilibrium constant expressions. Okay, let's get some practice. All right, let's go to exercise number 1. Let's just get some practice writing our equilibrium expression. Of course, I give you the answers down below to the right. It's simply asking us to write the constant equilibrium expression for the following reaction. So take a look at the reaction, and we set it equal to K. Really quick, I'm noticing that there's a lot of gases here. In fact, every single substance in the reaction are gases. So if you really wanted to, you could do case of P, which is typically written when we're talking about gases. Okay, we're going to go ahead and set our equilibrium constant, set it equal to the numerator. We will have our products. So I have nitrogen dioxide. I'm going to go ahead and raise that to the 4th power. And I'm going to have gaseous water. Gaseous water. Remember, if it's a pure solid or a pure liquid, it does not appear in the expression. Is gas either of those? No. So it will be included in the expression here. So I put the concentration of water and I raise it to the stoichiometric coefficient. All right, and then our our reactants go down in the denominator. Ammonia raised to the 4th times oxygen to the 7th. All right, so hopefully you're pretty comfortable at this point with being able to write equilibrium expressions, as we say. All right, let's try number 2. All right, it says write the expression for K and Kp for the following processes. Now, here's the thing. If you go back and read the problem, it says exercise 2, equilibrium expression for heterogeneous equilibrium. Remember what hetero means, you guys? Hetero means 2 or more phases are present. So 2 or more phases. Phases meaning solid, liquid, gas, okay? So if you didn't know that, or if it was a quick review, that is going to, we need to pay attention to things like that when we're doing and writing our equilibrium expressions. All righty, let's go ahead and do A. The decomposition of solid phosphorus pentachloride to liquid phosphorus trichloride and chlorine gas. Now, with this exercise, it wasn't as convenient as the first one. They did not actually give us the reaction. So in this particular case, we need to write the reaction out. So let's go ahead and do A really quick. All right. The decomposition of solid phosphorus pentachloride. So phosphorus pentachloride. And this is important when you include your states of matter, solid. And that is going to liquid phosphorus trichloride and chlorine gas. So this is when I would write my arrow, but because we're on equilibrium, let's draw a double arrow, okay? It's going to phosphorus trichloride, and it's a liquid, and chlorine gas, Cl2, gas. Most diatomic molecules are gaseous. All right, so look at our rules above. So if you scroll back up, bear with me. You scroll back up and look at some of the rules that we have to follow when we're writing our equilibrium expression. Go ahead and take a second and tell me which ones we are not going to include in the equilibrium expression for this first reaction. I know that I'm not going to be including this one nor this one in my reaction. So K equals the concentration of chlorine gas to the 1st power. By the way, I apologize. This reaction was already balanced, but that is definitely something you need to check. Remember, we raised coefficients to the concentration of that substance, so make sure it's balanced. I forgot to do that, but thankfully it is. So this would be our equilibrium expression for the first reaction, okay? And we see that chlorine is a gas. So if you wanted to say this, you could also say this, case of P. And remember, we use P for gases. What does P stand for? Partial pressure of gases. And we do have a slightly different writing convention. When we're setting up the equilibrium expression for gases, instead of using brackets, we oftentimes use parentheses. So you would say the partial pressure of chlorine and close it off to the 1 power. There we go. So either one of these would be acceptable for the equilibrium expression for A. Now let's do B. Deep blue solid copper 2 sulfate pentahydrate is heated to drive off water vapor to form white solid copper 2 sulfate. Again, you need to know how to write formulas. You need to know how to balance equations. Super important here. If you need to, put me on hold and write this reaction on your own and balance it to see if you got what I got. Okay, take a look here. Everything looks balanced except for, let me go ahead and just write it here. I have to put a 5 in front of this water molecule and go ahead and double check. And to me, it looks good. By the way, just let me add a little extra tidbit here. It says that this reaction is heated. So if you want to represent that this reaction was heated in your chemical reaction, remember above the arrow, you could put heat. It's not required at this point, but that's always for good measure to be super accurate and to represent the reaction truly as it's happening. Okay, so go back up, look at your rules. What will we not include in this equilibrium expression? That's right, solids are not to be expressed. And if it's gaseous, okay, if it's gaseous, it still can be expressed. Remember, if it's gaseous, that does not mean it's liquid. So the language here, just slow down and make sure you read the language correctly, because that could be an easy point lost if you don't pay attention to those things. All right, so again, solids are not expressed, so I'm not going to include this one, nor will I include that one. So how would I write my equilibrium expression? Set it equal to K, and I would put H2O in brackets, and I'd raise it to its coefficient, okay? But I will mention here that it is gaseous water. It is vapor. So because we're dealing with a gas, it would probably be more appropriate to write the Kp value. So again, that's still an equilibrium expression. You're just putting P down there to say, hey, I'm dealing with gases here, okay? At which point we do have a slightly different writing convention. Like I mentioned earlier, instead of using brackets, we will use parentheses. So you would say the partial pressure of water closed off raised to the 5, okay? Does that make sense, you guys? All right, you guys, those are the first 2 pages of our notes. So I'm going to go ahead and stop here, and we'll pick up on page 3, just a continuation of where we're headed. All right, thank you so much for joining.